Welcome to our lecture on dependent samples t-tests. So last week we did independent samples t-tests where we're comparing two groups of, well, independent samples where those two samples have nothing to do with one another. They don't impact the other. One score or measure on one of the samples does not affect the other. However, with dependent samples t-test, that's all thrown out the window. So in your book, dependent samples t-tests are referred to as related samples t-tests, but I just prefer to call them dependent. But if you're using the book, if you're reading that and you're seeing a related over and over again, just know that dependent and related samples t-tests are the same thing. Anywho, so again, like I said, with independent samples t-test, which we covered last week, the groups had no impact on the other. It was two separate groups of people, like our class and Professor Greenwood's class, or dog lovers and cat lovers. Those are two separate groups of people and they don't overlap. The people that are in our class are not also in Professor Greenwood's class. I don't know anyone who would take stats twice in the same semester. That seems a little woo. But anyway, people who claim to be dog lovers, they might also be cat lovers, but in the terms of our experiment and our personal example, it's you either are a cat person or a dog person. There is no, well, I like them both, although I do. But anyway, you're a cat person or a dog person, and we compared those groups as if they are separate from one another. They're exclusive of one another. So you can't, in that example, you can't be a dog person and a cat person. You're picking a side. So that would be dependent samples, or independent samples, excuse me, where they're completely separate. There's no overlap. There's no, you're either in one group or the other. They're not influenced by the other's responses, scores, anything like that. But dependent samples tests are different. They do rely on another sample. So there's several different examples of situations where you would use a dependent samples t-test, which I'm going to go over right now. So first, different research designs, I should say, that could use dependent samples t-test would be a repeated measure design. So this is known as a, excuse me, a pre and post test. Also, you can kind of think of it as before and after. So if I were to give you guys a final for statistics on day one, I'm going over the syllabus and I'm giving you the syllabus, like here's my expectations. Also, hey, here's an exam that's covering all of the content that we're going to cover in this class. I give you the final on the first day. And then with repeated measures designed with a pre and post test, between the pre and the post, you kind of expect there to be, well, pre and post what? What's it before and what's it after? It's the treatment. It's something that you're expecting to have scores increase or decrease based on this treatment. So if we're going to do a pre and post test with, I'm going to give you a final of statistics on day one of the class, and then I'll give you the final on, the normal final date, at the end of the semester. The treatment that's going to happen, that's going to occur between the first day and the last day of this class is going to be taking the class itself. You're actually going to learn the concepts of statistics, learn how to, do the things that are on the final, understand it, hopefully, knock on my whiteboard. But essentially the treatment in this case, the pre and post that we're referring to, it's pre day one of the class is the pre-test, which is before taking the class itself. And the post-test, the second time you take this final, is going to be post taking the class. The last day of class, we've already gone through it. So the treatment here is just going to be you taking the class. And in this particular instance, with the pre and post-test design, we'd expect you guys to have higher grades on the post-test of the final. You're having, you took the class, you probably should score higher on the final at the end of the semester than you did on the same final before you learned any of the stuff anyway, if I'm doing my job. But, excuse me, my goodness, I need to drink some coffee. But that would be a repeated measures design. So with the dependent samples test, keep in mind that those two scores, those two groups are dependent on one another. The two groups we have here are your scores before you took the class. On day one, you take the final and all the exam scores, the average exam score on the first day of class versus the final exam score on the last day of class. Dependent samples, you're still the same people. You know, it's still the same 29 of you, 30 of you, 50 of you, however many people are in the class that you're doing this for. It's still the same group of people. It's just the scores are different now, or it's just at different points of time that you're taking this exam. So we still have two groups, but with dependent samples t-tests, it's not, oh, you know, the pre-test, it's not, oh, I'm going to compare test scores on the first exam to Professor Cooper's class and compare it to Professor Greenwood's class or Professor Birkin's or anyone. It's going to be literally the same people. It's just at different points in time. So that makes it a dependent sample because it's not using independent samples. It's not separate groups of people. The scores that I'm seeing should be changing based on what my hypothesis is. So I'm expecting to see you guys have higher test scores after taking the exam the first time. You know, the second time you take the exam, I'm anticipating to have higher scores because you have actually learned the material, etc. So another research design that uses dependent samples t-tests are within subjects design. So this is similar to the repeated measures, except there doesn't have to be a treatment. And in the case of the example we went over, remember that treatment of what was going on between the pre and post test there was taking the class. That doesn't necessarily have to be present for just a within subjects design. Now, within subjects design is referring to many things that use dependent samples t-tests. It's essentially saying that the same participants are experiencing both conditions of an independent variable. So if we were to have, let's say that we were going to give every student the opportunity to take notes using a laptop or a computer or whatever, and longhand by pencil and paper or whatever, you know, your preferred writing utensil is. We're going to give two groups of participants, you know, the assignment to either take notes on a lecture on the laptop, and the other part of the participants to take notes on just pen and paper. Then if we just left it at that, that'd be independent samples t-test. Maybe we're gonna see, oh, you know, who retains more information. Maybe we give each of these groups, the longhand note takers and the laptop note takers, maybe we give them each the same test based on the material that they're taking notes on, and we compare their exam scores. If we just left it at that, that would be independent samples t-test. There's no overlap. There's no, oh, well, I'm gonna take notes with the laptop first, and then next week I'm gonna take notes using, you know, pen and paper, writing out my notes. If we don't do that, if we don't switch the conditions, it stays independent samples t-test. However, that's not what our lecture is about today. We're talking about dependent samples t-test. So for dependent samples t-test, again, all the participants experience both conditions of the independent variable, the thing that's changing between in this experiment, in this particular study. So the thing that's changing is, are you taking notes using a laptop or using pen and paper? So when we have to have all participants participate in both conditions of that independent variable, that means, okay, maybe half of our participants are doing laptop note taking, the other half are doing longhand note taking, and then a week later, maybe we give them, you know, long enough time so they don't really remember the material, just to kind of, because we'd have to do the same material to be lectured on, to just make sure that it's just for better research methods, it needs to be the same material. So maybe we wait a little longer than a week. Maybe we wait a month, call them back and say, okay, now last time you were taking notes using a laptop, now you're going to be just using pen and paper. And for those people who started by taking notes with a pen and paper, okay, now you're going to be using a laptop, take notes on this hour-long lecture or whatever the case may be. And then we're going to give you a little quiz or a little exam on it. We're going to test you. That is a within subjects design. The same participants, again, it's the same people coming in, and half of them started with the laptop, the other half started with pen and paper. And then after a month, they come back and they switch. Those who started with the laptop now are taking notes, pen and paper, and those who started with the pen and paper are now doing the laptop. Same people, it's a within subjects design. They're experiencing both conditions of the independent variable. Another example of research designs that use dependent samples, t-tests, would be a matched pairs design. So this is where participants are selected and matched with someone with similar characteristics. These characteristics can be something that the researcher determines. Maybe you're looking at, mother and daughter, how are, maybe neuroticism levels over time compared with a mother and daughter? Or, we are taking Latinx people, and we are going to pair them as like a 22-year-old Latina with another 22-year-old Latina. You're matching them with people that are similar characteristics. So maybe that can be complete strangers, just two similarly aged, similar ethnicity people, and you're seeing how their scores on something are changing. Maybe neuroticism over time, maybe stress, maybe adaptability, I don't know, whatever your test is looking at. But you're taking groups, you're matching these people in your study to other people that are similar. Now, again, this could be just complete strangers to people of the same age or ethnicity or gender or whatever, or it can be, I'm looking at, family relations. So that can also use a matched pairs design. Maybe you want to see, like I was mentioning earlier, a mother and daughter pair, or a father-son pair, or a mother-son pair, whatever. But these groups, this matching can occur experimentally, which is where you're just picking people based on characteristics like the same age, the same weight, the same ethnicity, the same whatever, the characteristics that the researcher is determining. Or it can be done, like I was talking about, through natural occurrence. That's like more familial, family traits. So these are pre-existing characteristics that the researcher isn't manipulating. They're not saying, I'm going to pick out all the 22-year-olds. It's going to be, I'm going to pick out mother and daughter pairs. Their age, I have no impact on that. I didn't tell the mother when to give birth to her daughter. That's intense. So that would also use a dependent samples t-test. So to do a dependent samples t-test, now we kind of have an idea of when to use it. So again, that pre and post test, that's something that I really like to use a lot. I feel like it's pretty easy to grasp. We're very familiar with the idea of like before and after tests. So pre and post test follows that same thing. But to do this, to get to the nitty gritty of what a dependent samples test is doing, it's comparing the difference between these two groups. So we're subtracting the mean scores from one group and subtracting it from the other. So this is different. We're not with independent samples t-test, we're just comparing the straight up means and then comparing them on two separate conditions. So independent samples of dog lovers and cat lovers, we got the means from the cat lovers, we got the means from the dog lovers and compared them like that. With dependent samples t-tests, we have our pre-test test scores and our post-test test scores. We subtract them first. So, the first time you took the test, you got a 50%, 50 out of 100. The second time you took the final exam, you got, 75 out of 100. So we would do, 50 minus 75, and that gives us a negative 25. And then we start working with that data. So dependent samples t-test, when we're calculating them by hand, is done through difference scores. Again, the difference of just one group minus the other. One individual score the first time minus the same individual score the second time, or the first condition they're in minus the second condition they're in, whatever that may be, whatever our test is setting it for. So as a practice, let's kind of get an idea of what dependent samples t-tests look like. So a researcher is testing how a teacher's supervision influences the time it takes elementary school students to read. 2 6-minute reading sessions were scheduled. The time students spent reading in seconds were recorded. Okay, so there's they're reading for 6 minutes, they're being timed for 6 minutes, and each student as they're reading is being timed how long they're actually reading. So they're looking down, they're actually, looking at their papers, they're not on their phones, they're not, poking other kids or whatever the hell it may be. So each student reads in these 6-minute sessions, except there's a difference. One, there is a teacher supervising, so there's a teacher in the room kind of looking over, and the other where there's no teacher, just, it's just anarchy. So now let's test whether the reading times differ when our alpha, our significance level, is set at 5% or 0.05. Okay, so here's some data. So keep in mind we had 2 groups. Everyone's reading in 6-minute sessions. All these kids are reading, all 8 of our kids here we see with participants 1 through 8, that's 8 children. They're reading with a teacher present and a teacher absent. The teacher's not present. And so remember these numbers, these 220, 210, 245, 220, 215, the numbers in the columns for present and absent represents the number of seconds those kids spent reading in a 6-minute span. So for participant 1, that student spent 220 seconds reading while a teacher was present and 210 seconds reading while a teacher was absent. So I mentioned how with dependent samples t-test, it deals with different scores. We're subtracting one score from the other, one condition from the other. So here's what I've just done. So we have 220, the first condition, minus 210, the second condition. We have 245 minus 220 here. We're just taking each of the scores from the conditions and subtracting them. So 215, the present score minus the absent score gets us a difference score of 20. 260, the present score minus 265, the absent score, -5, and etc. down the line. So this is what we have to do first before we start finishing or continuing on with dependent samples t-test. We have to find these difference scores. So step 1, here we go. We got to get back into our 4-step process of null hypothesis testing using now a dependent samples t-test. Keep in mind that every statistical test that we use has slightly different hypotheses, has slightly different formulae to calculate our test statistic, has slightly different meanings when we say we're rejecting or retaining the null hypothesis. So here we go talking about dependent samples t-tests. So keep in mind that what we're doing is we're subtracting one score from the other. We're finding the differences between these groups. That's a dependent samples t-test. What's the difference between this group and that group? So when we talk about our null hypothesis, that mu d there is the mean difference scores, the mean difference, d for difference. So if we're not, so the null hypothesis, remember, is saying there's no relation, there's no difference, there's nothing going on here, there's nothing to see here, officer, I'm innocent. So when we have a null hypothesis for a dependent samples t-test, if there's no difference in these groups, if they're the same, we'd expect the difference in them, if we subtract one from the other, to be 0. If we take the exact same number, 5, let's say, and subtract it by the exact same number, 5, we would get 0. So that's why our null hypothesis for dependent samples t-tests is the mean difference score is equal to 0. So it gets a little weird, but just as long as you know that a dependent samples t-test is just looking at the difference between scores, the difference between conditions, literally the difference, one minus the other, it makes sense that our null hypothesis is equal to 0. Keep in mind, the first thing we did before we even got to this slide was, oh, let's find all the difference scores. We have 220 minus 10. We were taking, or 220 minus 210, I should say. Ooh. But we were taking the scores for one condition and subtracting them from the scores of the other condition that each participant, participated in. So anyway, the null hypothesis for this test is saying that there is no difference in time spent reading in the presence of a teacher versus in the absence of a teacher. The null hypothesis is saying that the students were reading this approximately the same amount of time, regardless of if the teacher was there or not. And of course, we have our handy dandy alternative hypothesis, which is basically just saying the opposite. So there is a mean difference in the time spent reading with the teacher in the room and without the teacher in the room. And again, that mu d refers to just the mean difference. Okay, so we have our hypothesis stated. Typically, when we have null hypotheses for dependent samples t-tests, are gonna follow this same rule. It's different from one sample tests, be it T or Z, where we had our mu equal to a particular number. We don't have access to the population here. Remember, it's a t-test, so we're only dealing with samples, especially when we're talking about dependent samples t-test or independent samples t-test. We're not looking at a one sample t-test where we're comparing one sample to a population. We're looking at independent, or in this case, dependent samples. All we got are samples. We don't have any information about the population except just what we're extrapolating from these samples that are in the problem. But I digress. So we have our null and alternative hypotheses stated here. So again, our null hypothesis is saying that the mean difference will be equal to 0. There's no difference between the time spent reading with or without the teacher in the room. And the alternative hypothesis, again, is saying the opposite. There is a mean difference in time spent reading with and without the teacher in the room. So now we have to set the criteria. As per usual, our alpha is set at 0.05, but since this is a t-test, we need to calculate the degrees of freedom, as we do for all friggin' t-tests. So again, just like how there is a slightly different way to take the, to calculate degrees of freedom for independent samples t-tests and for one sample t-tests, there's a slightly different notation for dependent samples t-tests. However, it's similar to one sample t-test in the sense that you're taking the sample size of the different scores. So just how many different scores do you have? And you subtract 1 to find your degrees of freedom. Now keep in mind that there were 8 different scores. There were 8 different participants. Here, I'll just go back up really fast. There were 8 different participants here. We have 8 different, we have 8 different scores. So that gives our ND, our sample size for our different scores, equal to 8. And we subtract 1. So our degrees of freedom for this particular problem is going to be 7. Something's going on outside, but it's nothing. Pay no mind. Anyway, so we have our degrees of freedom. We have our alpha set at 0.05. We're going to have this a two-tailed test. There are cats fighting outside. Calm down. Anyway, so we have our two-tailed test because it is the different scores is not equal to 0. We don't have our different scores are greater or less than 0. It's just not equal to 0. So it's a two-tailed test. And I have my handy dandy T table here. So if you want to look along with me, again, our degrees of freedom is 7, and our alpha is set at 0.05 in 2 tails. So that gives us, that gives us our critical value of plus minus 2.365. So we have step 2 done. We know that if our test statistic that we calculate from this problem, if it is greater than positive 2.365 or less than negative 2.365, we're going to reject the null hypothesis. Meaning, again, if we reject the null, that's basically retaining the alternative hypothesis and saying when we reject the null, hey, the mean difference in number and how long students spent reading with and without a teacher present, there is a difference there if we reject the null. Okay, so now we have to compute the test statistic. So pretty much get used to here on out that computing the test statistic is going to come in multiple steps. I mean, it kind of already has been, always has been, but you know, t-tests seem to really get persnickety about multiple different steps we have to take before we finally get our test statistic. So first we have to compute the mean variance and standard deviation of the difference scores. That is why we do the difference scores first. Just get those out of the way, because those are going to be the numbers that you are using to analyze everything with the dependent samples t-test. You're not really comparing, you're not taking the means of group 1 and comparing it to the means of group 2 like you do for independent samples t-tests. No, we're subtracting them from one another, and those scores we get from subtraction or difference scores, that's what we use to do our analysis for a dependent samples t-test. So once we have the different scores, which we've already done in this problem, we're going to find the mean, the variance, and the standard deviation of those. Next, we're going to find the estimated standard error for different scores. Look at that estimated. Remember, when we're dealing with t-tests, which is primarily dealing with samples, it's always going to be estimated because we don't have the population information. So it's estimated. We can only estimate with the sample. So after we calculate the estimated standard error for the difference scores, then we compute the test statistic. Okay. So these scores I have here, that 10, 25, 20, -5, 25, -10, 30, and 25, those are the difference scores from before. So that is when we took the length of time in seconds that the students spent reading with the teacher present minus the teacher absent from the room. These are the scores that are from that. So just to kind of refresh your memory, you know, we had 10, 25, 20, -5 down the line. We have that same thing for this particular problem. So those same numbers in our difference scores in that far right column are the same numbers we're using to calculate the mean, variance, and standard deviation. So again, for mean, we know how to do that. Mean is not going to change regardless of how you slice it. If you're dealing with a population or a sample, a t-test, or a t-test, a z-test, a NOVA, etc. Mean is mean. You know, your mean is just a mean mumbo jumbo. So you're just going to take all the scores and divide it by the total number of scores you're adding together. So there are 8 scores here. So we're just adding them all up and dividing by 8. So when we do that, we get 120, and we're dividing by 8. That gives us the mean of our difference scores to be equal to 15. Okay. So the mean of our difference scores is equal to 15. So mean of the difference scores is equal to 15. All right. Moving on up. So next, this is all still the first step of calculating the test statistic for a dependent samples t-test. We've done the mean. Now we got to do variance. We got to have the variance. So variance is a little different for dependent samples t-test. Now for this, we still use that. Notice in the denominator of the variance equation of the sum of squares is divided by the number of difference scores minus 1. That's similar to how we calculated sample variance back, you know, what seems like ages ago. Remember that for when we're calculating a sample variance, it was always the sum of squares divided by n minus 1. Whereas if we were just doing a population variance, it was sum of squares divided by just n, our population size. Again, dependent samples t-tests, we're dealing with samples. So get used to that denominator of sample size minus 1. Okay, so our sum of squares is equal to the, excuse me, the sum of the squared difference scores minus the sum of the difference scores squared divided by the number of difference scores. It sounds like I'm repeating myself. It seems like these are the same things, but I assure you they're different, and I'm going to show you. And I've just kind of written out on the bottom in the 1 and the 2, just what these notations are essentially translating to. So this sum of squares, which is this SS here, again, is equal to the sum of the so sum is that sigma of the difference scores squared minus the sum of the difference scores. Square that number and divided by the number of difference scores. And we plug that sum of squares, the number we get from this, into the equation to finally get our variance. So we plug in the number from this to get our sum of squares, and we take that number and ploop it on into the numerator of the variance equation and divide it by the number of different scores minus 1. All right, so to do that, we have our different scores of 10, 25, 20, -5, 25, -10, 30, and 25. Okay, so those were our different scores. Those are just uncut, unfiltered, pure different scores. That's just taking present, the number of seconds spent reading when a teacher is there, minus the number of seconds spent reading when a teacher's not there. That's what that column on the left is representing, just the pure different scores. The column on the right, that d squared, is when we square those. So 10 squared is 100, 25 squared is 625, 20 squared is 400, -5 squared is 25, etc. So when we have the sum of the different scores, that's just referring to 10 plus 25 plus 20 plus, or well, -5 plus 25, -10 plus 30 plus 25. And that sum of the different scores is equal to 120. The sum of the squared different scores, this sigma d squared, is referring to when we add up all of the squared different scores. So 100 plus 625 plus 400 plus 25, etc. So I have these here below the columns that they're summing, essentially. So let's go back to that equation where it seemed like it was essentially the same. So we have our variance for the different scores is equal to the sum of squares, the sum of squares divided by the number of different scores minus 1. And to calculate the sum of squares, we have to take the sum of the squared different scores minus the sum of the different scores squared divided by the number of different scores. Whew. Okay, so let's just go through this slowly. I plugged in this formula here. So here we have the sum of squares. 3,400 is that first number, the sum of the squared different scores. So here are our squared difference scores here, 100, 625, 400, 25, blah, 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 blah. And when we added those all together, we had 3,400. Boom, that's where we got this number. Minus, notice the parentheses here. Notice that it's just referring to the sum of the different scores, and we take whatever number that sum is and square it. So the sum of the different scores, just the pure uncut sum of those bad boys, is just 120. So we have, our 10 plus 25, etc. That's where we get that 120. And we square that number. Excuse me. We square that number and divide it by the number of different scores. Okay, which is 8. The 8 never changes. That is the number of different scores we have. All right. So 3,400 minus 120 squared divided by 8. That's when we plug in the numbers to this sum of squares formula. Okay, so let's kind of simplify it. So 120 squared is 14,400, divide by 8. Once we divide that number by 8, it gives us 1,800. So 3,400 minus 1,800, our sum of squares at this point is equal to 1,600. Okay, that's just the first part of variance. So now we take our sum of squares, our variance for the sum, our variance for the different scores, and we plug in the numbers we have. So we have our 1,600, our sum of squares. So we take that and plug it in, and then divided by, we plug in the number of different scores we have. So number of different scores is 8 minus 1 minus 1. So 1,600 divided by 7 is rounded off to 228.57. So there, we have our variance for the different scores, which is 228.57. So we have our variance for the different scores equal to 228.57. Okay. Now, keep in mind, we're on variance right now. Next, we have to do the standard deviation of the different scores. Well, that's easy. once we've done the variance, which is frankly the biggest pain in the ass of this whole thing, once we've done that, it's easy to find the standard deviation because we just take that number of our variance for the difference scores of 228.57 and we just square root it. Again, I've written out the formula as well as like the translation of what those things mean. So SD equals the square root of S squared D. So the standard deviation of the difference scores is equal to the square root of the variance of the difference scores. So we have the variance already, so we just take the square root of that, and our standard deviation of the difference scores is equal to 15.12, square root of 228.57. Okay, so step 1 of computing the test statistic is done. Nifty. Now we have to calculate the estimated standard error of the difference scores. We've had the mean, we've calculated the mean, variance, and standard deviation of the difference scores in step 1. Now we're going to compute the estimated standard error of the difference scores for step 2. Okay, so that formula is equal to the estimated standard error of the difference scores. That SMD is what that stands for. Is equal to the standard deviation of the difference scores. Hey, we have that, divided by the square root of the number of difference scores. Okay, so the standard deviation of the difference scores is 15.12 divided by the square root of the number of difference scores. Again, that the number of difference scores we have is just the same. It's 8. So 15.12 divided by the square root of 8. That gives us the estimated standard error of the difference scores equal to 5.35. Okay. That's step 2. Done with that. Now to compute our test statistic, the final step of calculating the test statistic, our T obtained, so our obtained T statistic, is equal to the mean of the difference scores minus the null hypothesized mean of the difference scores divided by the estimated standard error of the difference scores. So here's where it all comes together. Remember that we calculated the mean, variance, and standard deviation back in step 1. Here's the mean. Now we need that again. We calculated the null hypothesized mean of difference scores. That's already the null hypothesized mean for difference scores for dependent samples t-tests never changes. It's always that the score is equal to 0. The difference, if the groups are the same, which is what the null hypothesis is essentially telling us, if the groups are the same, when we subtract one from the other, it's going to be equal to 0. 5 minus 5 is 0. 7,012 minus 7,012 is 0. Any number that's the same is going to be equal to 0 when you subtract it from itself. So our null hypothesized mean of difference scores is equal to 0. And divided by the estimated standard error of the difference scores. Hey, we got that too. So finally, step 3 of computing the test statistic, the T statistic. Now all that's coming together. So we found the mean of the difference scores way back in the day. That was equal to 15. Remember, we just added up all the different scores by subtracting. Those different scores were just, for each individual participant, the number of seconds spent reading with the teacher minus the number of seconds spent reading without the teacher. All those different scores, we added those together, divided by 8. That gave us our mean of 15, minus 0, because that's the null hypothesized mean of the different scores. So 15 minus 0, divided by 5.35. That gives us our T statistic, our obtained test statistic, our obtained T test statistic of 2.80. So our T here is equal to 2.80. Whew, there we go. Now we make a decision. So now we're comparing our obtained test statistic, that 2.8, to our critical T value, our 2.365, which again, we determined through the T table. Okay, with that, since our test statistic is greater than our critical value, 2.8 is indeed larger than 2.365, we would reject the null hypothesis, which is saying, hey, there is a significant mean difference in time spent reading with a teacher in the room versus without a teacher in the room. We reject it. We're rejecting the null hypothesis, where the null hypothesis is saying, nah, they read at approximately the same rate. Nope, we're rejecting that notion. They don't read at the same rate when a teacher is in or out of the room. Just to kind of be a little more specific, I've simply taken the mean of each of the conditions here, 260, or excuse me, the sum. So, oh wait, no, wow, God, I can't even talk. This is the mean, yeah. So 260 is the mean for the present, 245 is the mean for the absent. If you want to be more specific with your rejection of the null hypothesis, instead of just saying they're different, you can say, oh, you know, these participants spent more time reading when the teacher was present as opposed to when they were absent. And the way I got that was, again, just calculating the means of each of the conditions by themselves, where present, in fact, did have a larger mean than absent. Yeah. Okay, so if you have any questions, keep in mind that you can still email me, you can still contact me. If you know, if your question is simple enough to where you think you could just handle it through an email, that's fine. If you want to have a Zoom meeting with me and actually, you know, talk to me face to face in this epidemic crisis, then you just still email me, say, hey, I'd like to set up more of a in-person, face-to-face conversation with you, and I'd be more than willing to talk to you about any questions that you may have, and not just about dependent samples t-tests, about independent samples t-tests. If you want to do a throwback and talk about one sample Z or one sample T, I'm also more than willing to do that as well. So I know that this isn't very helpful in terms of a recorded video. If you have questions, you'd just be looking at YouTube and like, okay, I have questions, but like, eh. But if you need to review, you can look over this video. If you've looked over this video and you find that you're still not figuring it out, just email me and we'll figure it out from there. So I am also now going to go over an example of a dependent samples t-test. So this would have been our group collaboration, so for if we had an in-class situation going on, but we don't, so here we are. So here's an example of a dependent samples t-test, another one. So a researcher wanted to compare longhand to laptop note-taking. Oh my God, this sounds so familiar. So there were two conditions: taking notes on a lecture using a laptop, and the other condition was taking notes on a lecture using a pen and paper. After 30 minutes, this 30-minute long lecture, participants were quizzed on the knowledge and their scores were recorded. Participants then switched conditions and took notes on a different lecture. So in this situation, we're talking about a different lecture. So participants' quiz scores following this lecture were also recorded. So same situation, they had 30 minutes taking notes on a different lecture and their quiz scores are recorded. That's what we're comparing here. So now we want to know if there is a difference between laptop and longhand note takers, their quiz scores, when our significance level is set at 0.05, when alpha is set at 0.05 or 5%. So we got to know the difference scores first. So for us to know the difference scores, first we kind of got to know the scores themselves. So here we are. Let's say that this was, I don't know, a 10-question quiz, and these numbers represent how many they got correct. You know, that participant 1 in that first row got a score of 8 when they were taking notes using a laptop, and a score of 6 when they were taking notes just using a pen and paper. So those are our two conditions, laptop or longhand. This is a within subjects design. Each participant is experiencing both conditions of note-taking, laptop and longhand. So we got to start with the difference scores. So 8 minus 6 is 2, 10 minus 3 is 7, 6 minus 8 is -2, 3 minus 2 is 1, 5 minus 7, -2. I don't mean to insult your intelligence, especially since I'm just going to go to the next slide and boom, there they are. It doesn't really matter which, just to make this point, I know that you guys might be kind of questioning this later. It doesn't matter which group you subtract from which. Some might make more sense, like maybe you want to do, oh, post-test minus pre-test. Maybe you want to do pre-test minus post-test, but ultimately it's not really that big of a concern as in terms of which you subtract from. It can go either way. Okay, so we have our difference scores of 2, 7, -2, 1, -2, -1, etc. So these are the numbers we're working with. Those numbers in the far right column, this is where the magic's going to happen, MTV Cribs. So here we are. So we're going to state the hypothesis. Note that these are the same sets of hypotheses that were for the previous problem when we were dealing with the reading with or without a teacher present. It's just now we have a different problem, but the statements are the same. So for our null hypothesis, the mean difference is equal to 0. And for our alternative hypothesis, the mean difference is not equal to 0. Now, in terms of what this means, it's a little different because, again, we have a different problem. So in this case, the null hypothesis states that there's no difference in quiz scores between laptop and longhand note takers. And the alternative hypothesis is saying that there is a difference between laptop and longhand note takers' quiz scores. Okay, so step 2, we had 6 different scores. We had 6 participants, just to kind of throw you back. To get our degrees of freedom, we have to take the number of different scores minus 1. So we have 1, 2, 3, 4, 5, 6 different scores. So let's go back to this. So 6 minus 1 is 5. So our degrees of freedom is 5 with a two-tailed test set at 0.05 for alpha. Again, if you want to follow along with me and look at your t-test table, 5 degrees of freedom, 0.05 in the two tails, 2.571 is going to be your critical value, plus or minus 2.571. Again, if our t statistic is greater than if our t statistic is greater than 2.571, or if our t statistic is less than negative 2.571, we would reject the null hypothesis. If our t statistic falls anywhere between negative 2.571 and positive 2.571, anywhere in that in-between woobly area that I'm making with my hands right now, that's going to be where we retain the null hypothesis. Don't get your p-values and your test statistics confused. Remember, with a p-value, we're comparing p-values to alpha, that 0.05. If your p-value is less than 0.05, you would reject the null. If it's greater than 0.05, you would retain the null. But with test statistics, it's different. If it's greater than the absolute value of the critical value, then you'd reject the null. If it's less than, if your test statistics absolute value is less than the absolute value for the critical value, if it's less, you would retain it. It's a common mistake, so don't feel bad if you do that mistake, but just, you know, chickadee check yourself, because I don't want you to wreck yourself. So first, you know, we have our critical value set, we have our null hypothesis, our alternative hypothesis. So now we get into step 3, which is computing the test statistic. So step 1 of computing the test statistic is to compute the mean, variance, and standard deviation of the difference scores. All right, so to find the mean, we just add them all together and divide it by the number of different scores. So 2 plus 7 minus 2, That gives us 5 divided by the number of different scores, which is 6. And that is the mean of our difference scores is equal to 0.83. All right, we'll use that later, but we have the mean taken care of. Cool. All right. Now the variance, again, back to this fun time, back to this slightly confusing, and if you get confused by this, it's okay, but just follow along carefully. So here we are at the variance of the different scores. Again, same stuff, same formula, or formulae, but now let's plug in the numbers for this equation, or for this problem. So here are our different scores, 2 plus 7 minus 2 plus 1 minus 2 minus 1. That gives us the sum of the different scores equal to 5, which is where we put right here, that sum of different scores. And then the sum of the squared different scores, here are our squared different scores, the 4, 49, 4, 1, 4, 1. Again, 2 squared, 7 squared, negative 2 squared, etc. we add those up, and that gives us 63. So that's where this 63 is coming from. This sum of the difference, or the sum of the squared difference scores. That's this. The sum of the difference scores squared is that. All right. So again, we're going to just start with this sum of squares formula because we need to calculate this before we get our variance. So that's 63, the sum, excuse me, the sum of the squared difference scores, 63, minus the sum of the difference scores, 5, squared, divided by the number of difference scores, which is 1, 2, 3, 4, 5, 6. All right, so that simplifies to 63 minus 25 divided by 6. So PEMDAS tells us that 25 divided by 6 is 4.17. So then we do 63 minus 4.17, and that gives us 58.83. So our sum of squares is 58.83. And then we divide that number by 5, or 6 minus 1. So our variance for the different scores is equal to 11.77. All right. Now we know what's coming next. We know that the standard deviation is next, and that's possibly the easiest thing to calculate. So, well, once we've done this already. All right. So let's move on to calculating the standard deviation for the variance scores, or for the difference scores. What we do is we just take the square root of variance of the difference scores, and that gives us the standard deviation of the difference scores. So 11.77, once we square root that, that gives us 3.43. Boom, we have our standard deviation of the variance scores. All right, so now that we have that, now we're going to compute the estimated standard error of the difference scores, that SMD. All right, so we're going to take our 3.43, which was the standard deviation of the difference scores. We're going to divide it by the square root of the number of difference scores, which was 6. And that gives us 1.40. So square root of 6 is like 2.8 something or other, or something. But maybe not 2.8. Oh, let's see what exactly the square root of 6 is. All right. 6 square root, 2.45. Okay, so I was a little off. But 3.43 divided by the square root of 6 equals 1.40. So that is our estimated standard error of the difference scores, this 1.40. All right, finally, here we are at the final stretch. So to get our test statistic, our T statistic here, we take the mean of the difference scores, which was 0.83, which we calculated back in step 1 of this whole escapade, minus the null hypothesized mean of difference scores. For an for a dependent samples t-test, that null hypothesized mean of difference scores is always going to be 0. So it's just 0.83, our mean, minus 0, divided by the estimated standard error of the difference scores, which was 1.40. That we calculated back in step 2 on the previous slide. So 0.83 divided by 1.4 is equal to 0.59. Alrighty, nifty, bitchin', cool. So we have our test statistic. We have our T statistic here at 0.59. Now let's compare it to the critical values in step 4 to determine if we're going to retain or reject the null hypothesis. So our T statistic of 0.59 is less than our critical value of 2.571. It's not greater than positive 2.571. It's not less than negative 2.571. So it falls in that middle block where we retain the null hypothesis. Again, if we were to draw a normal distribution where on one end was negative 2.571, and on the other was positive 2.571, that 0.59 is going to fall in the middle of that number line, or of that distribution. If it helps you to think of it as a number line, then by all means go for it. But either way you slice it, we're going to retain the null hypothesis, meaning that there is not a significant difference between quiz scores for people who took notes on a laptop versus people who took notes with pen and paper. We retain the null hypothesis. Woo! All right. So the last thing I wanted to go over in this lecture was just going to be the estimated Cohen's d, the effect size. So to do this, we already have all the stuff. We already have all the information we need. Usually Cohen's d is easiest once we've already determined if we're going to retain or reject the null hypothesis, because the stuff that we need to calculate Cohen's d, we've already done to calculate the t statistic in the first place. So the mean of the different scores, if you recall, that was 0.83. Again, just adding all those different scores and dividing by 6, the number of different scores there were, divided by the divided by the standard deviation of the different scores, which was 3.43. Once we do that division, we get 0.24. So our threshold for Cohen's d is anywhere between 0.2 and 0.8 is going to be considered medium. So if we're going to stick to that, this is a medium effect size. 0.24 is a medium effect size. But since it's pretty on the cusp, since it's pretty close, I like to kind of say it's a small, medium-ish effect size. But so long as you either say that, or you can just say a straight up medium, that would still be correct. But again, it's a medium effect size. Let's say with medium effect size. If this were negative 2.4 or negative 0.24, that would still be a medium effect size. When you have Cohen's d, depending on if you have a negative or a positive, that doesn't impact the strength of it. Just look at the number itself, the absolute value. That 0.24 has the same strength as negative 0.24. It doesn't matter. It's still going to be medium effect size. Okay. So that is all that I have for you for for dependent samples t-tests. Again, if you have any questions, be sure to email me, let me know. Just tell me. I don't know you have questions unless you ask me. So I am still available. So please, oh please, let me know if you have any issues or problems. And I'll see you next time. Or rather, you'll see me next time. I'm not really seeing you. So.